All the recordings are on YouTube. And I've put the links on this website. For which I've given you the link. So there's a new tab where you can see the recordings. So let me just quickly summarize what we have done yesterday, not go through all of it, but through the sort of the measurement of central tendency and measurement of variation, and just simply write down the sort of the equations that we used for that. So we said we've got a data set. I'm not bothering you again with the 1, 2, 3, 4, 5. You know that. We set the mean of the data, mu, equals just simply the sum of the observations divided by the number of observations. Very simple, yeah? And we've done the median, we've done the mode, but that's basically the shorthand form for the average or the mean of our data, There's a reason why I repeat that, because we will soon do a little modification. We also said the variability is often expressed as the variance, abbreviated with this sigma square. And we can actually write this as it is the sum of the observations minus the mean squared divided by n, by the number of observations. Yeah, we did that. And we said variance has the problem of it does not keep the unit, because the unit would be squared to the initial unit. Therefore, we use the standard deviation. And we said the standard deviation, sigma, equals just simply the square root of the variance. Yeah, these were the 3 equations which you probably want to bear in mind when you do the first part of the assessment. So these are the useful equations, right? And I showed you how we can deal with these equations in Excel, how you can easily calculate the values for these things. So that was from our data set. And this data set basically was all the data that we have. But you see, there's a slight problem with it. If we are totally honest, nobody, absolutely nobody, gives a flying flamingo about these measurements. Let me put this into context. Let's say I take measurements. I measure the height of, say, 10 people here, right? Measure the height. And I record that. Who cares? Who gives a damn about it? You know, nobody. I give 5 people, or here, I give you a drug that reduces blood pressure. And I record that. What is your blood pressure after the drug? Who cares? It's just 5 people. or 10 people when I measure the height, or something like that. It is selected people. Nobody is interested in that. I mean, we might be interested to see, oh, yes, okay, good. It's quite interesting. We can measure the height of 10 people. So what? So why the hell are we doing that? Well, the idea basically is that we say these 10 people where we measure the height, or the 5 people with the drug, something like that, we take them as representative of a wider population. Yeah? So, I say, for example, we turn that on its back, and we say, I want to know what is the average height of an apprentice who is doing clinical trials. Yeah? I'm going away from the sort of the small group here, and I say, I'm not interested in the small group. I want to know the big population, the big picture. But I can't measure every apprentice, probably even at the same time of the day. So I need to take a small sample. And this sample is part of the wider population. I want to know whether this particular drug that I just gave you is not just working on you guys. I want to know whether this drug is actually working on, well, I mean, what would be the bigger population?
Target audience.
On the target audience, what would be the target audience? If I give these 5 people here the drug, what would be?
The wider population, I guess.
It's the wider population, yes. In this case, it probably would be everybody in the UK that I have my target audience? No. Just, yes, I could say it would be probably apprentices. There could be some quality that makes these makes the apprentices very sort of resilient against this drug. Or I could say there is a certain age group only here. So I could say I need to limit it and then say, actually, I'm interested in a certain age group, maybe not just apprentices, it could be car mechanics as well, or something like that. Yeah. So I need to be careful what I define as my population. But usually what we say is we just simply have a population. So that's the population. And from this population, we just simply take a sample. And we say, well, as long as the sample is representative of the big population, we just as well can use the smaller sample. We don't have to measure every apprentice. We don't have to give the drug to every apprentice. We just use this sample as a representative of the entire population. Yeah? Now here comes the kicker. What do we know about the population? What do I know if I measure 10 people, the height, what do I know about the population of apprentices? I don't know anything about them, right? No idea. That's a bit annoying, right? But wait a moment, don't I know anything about them? If I assume, and that is a big assumption, but if I assume that this sample is representing the apprentices, all the apprentices in the country, for example, maybe even in Europe, or maybe just in the UK, if I assume that this sample is a true representation of the wider population of apprentices, for example, then I can say, right, I can make some predictions about the population. I don't know for sure, but I can make predictions. And these predictions could be, for example, I take the sample mean, just simply the mean that we've calculated yesterday, and say this mean makes it quite likely that this is also the mean of the population. So I basically say sample mean is probably very similar to the population mean. So what I try to do is I try to sort of estimate the population mean. And here comes something in that people find incredibly confusing, but if you think about it, it's probably not so confusing. This estimate is always with a sort of a certain error, right? Could be right, could be wrong. And we need to sort of, in our heads, indicate that there might be an error because we are estimating things. Now, when we did our calculation of the mean yesterday, in this case here, this equation, is there any doubt, is there any uncertainty in it when we do this calculation? Was there any, was there any estimate in it? No, it wasn't. We were absolutely clear that was 100% what we got. But now we say we've got this really bizarre situation where we have to make an estimate of the population. If we measured everybody in the population, all, how many thousand apprentices would we have? Probably thousands. If we measured everybody, then it would be 100% clear there would be not a problem. Well, we can't do that. And in order to indicate that we are talking about the population or that we are talking about the sample, there are certain conventions which indicate immediately by a statistician or to a statistician that we are talking about a population or about a sample. For example, population will always be described as population. What's that? Population. A population has parameters. So population parameters. If somebody is talking about parameters, it means they are talking about a population. On the other hand, a sample has statistics. So if I tell you, find the statistics of the data, you know, we are talking about a sample. When I tell you, find the parameters of the data, you know we are talking about a population. A population is also, these parameters of a population are usually abbreviated by Greek letters. So a population would have a mean, mu, and for example, a standard deviation, sigma. Greek letters indicates we are talking about a population. What about the sample statistics then? How do we indicate that we are talking about a sample? Well, this is not Greek letters usually. And instead of the mean mu, which is now reserved for the population, it is usually for sample, we indicate the mean is given as something that's called x with a line on top of it. It's called x bar. How you do that on a document like Google or Word, where you have to use the equation editor. When the statisticians introduced these symbols, they probably did not think about how to print that on a computer. So X bar is a little bit awkward to write, but it is an indication. X bar is the equivalent of the mean. And what we can do now is actually we can say, instead of the population mean, mu, which we don't know and which we probably will never find out actually, because I can't measure everybody. Instead of this mu, I use X bar as an estimate. So how do we find X bar? Well, that's very simple. X bar is, in this case, oops, what am I doing here? Is just simply I take all the measurements of these 10 people, for example, xi, and divide it by the number of observations. It's exactly the same equation that I had up here, only that I called it up there mu, because there, yesterday, 1, 2, 3, 4, 5, were all the data that we could have. That was basically, we treated that as a population. Today, we treat them as a sample, still 1, 2, 3, 4, 5, a sample, but there might be more and more data around. Yeah, so we just pick these 5 numbers as representing our total population. So X bar is basically our best guess for our population. And if I measure them, I'll say, okay, 178 centimeters of these 10 folks here, or we take all of you guys so that we are totally inclusive, say 175, because we've got some people who might be a little bit more vertically challenged or something like that, right? I'm not looking at anyone. Then we say 175 centimeters. That is the mean of our sample And we think, well, that's our best estimate for the mean of the population as well, as long as the sample represents truly the population. Yeah? So it's the same equation. We can now, okay, we've got 175 as the estimate for the population. And I go back to this 10 people that I measured. Yeah? Now, just to be on the safe side, I measure another 10 people. Can do that, right? First, I measure up to here or something like that. And then I just simply randomly pick some more people, another sample, same size, 10 people. Something like that. And I measure again the height and calculate the sample mean. So first I calculated sample 1, and I got the mean for sample 1, x bar 1. Sample 2, I can do exactly the same thing, right? Can calculate the sample mean again from this different group of people. Question. Will it be exactly the same sample mean for the second sample? Oh, wait. Oh, I don't know. We got any tissues? It's a nice break, hey? For you to think, will sample mean 1 be exactly the same as sample mean 2? What do you think? No. Why not?
Very unlikely, surely.
Why?
Because everyone's a different height.
Ah. So okay, I take your point. They might be different in height, yeah, depending on who I choose. But of course, there is a problem now. Because if I use a sample mean to predict my population mean, I say, well, the population mean is probably similar to this one here, to this x bar 1, to the sample mean 1. And now you come along and throw a spanner in my thinking and say, wait a moment, I took another sample, and the sample mean that I have indicates that it is a different population mean. That's not fair. It might be similar, but it is inherently different. You're absolutely right. So which one is correct? In the first case, I say the population mean is 175 centimeters. In the second one, I say the population mean is 178 centimeters. Which one should I believe? Do you see the problem? Which one? Help me, help me. Did I make a mistake? Probably not. So what we can do is we just simply say we can never give a good estimate, a true estimate for the population mean. Can never do that, right? Because depending on the sample. That's a bugger. why don't we go home and just, pack up? And because if we can't do that, what's the point of the whole thing? We didn't make a mistake, but we can't estimate the population. And that is what we wanted. That's what we want to have. This observation that whenever we take a sample, the sample mean will be slightly different from the next sample, actually has a name. Does anyone know what it's called? No? This name, I absolutely hate it, but nevertheless, it's very common. What we observe here is called sampling error. Sampling error just simply says, whenever I take a sample, the mean will be different from the next sample mean when I take another sample. And this will be different from the next sample mean. And if I've got 100,000 sample means, then I've got probably 100,000 different means. I hate the word error because there is no error in it. We have done everything by the book. We have done every measurement exactly how we should do. I would like to change that to sampling uncertainty, because there's an element of uncertainty depending on who I pick, but it's not an error. But statisticians say it's sampling error. And to be absolutely clear, sampling error is a little bit like herpes. You just simply have it. End of discussion, right? You've got herpes. 80% of the British population are carriers for herpes. And the 20% others, I have absolutely no idea why they don't have it, because they should have it. And with herpes, I don't necessarily mean the sexually transmitted one. Herpes, the virus is, if you've got mouth ulcers and sores and things like that, that's all herpes, right? Sampling error is like herpes. You have it, and there's nothing you can do. Herpes is for a sampling error is for life, right? And you can't get away from sampling error. The problem, of course, is every time you take a measurement, you get another estimate for the population mean, which is annoying because we want to know what the population mean is. It's not good. Can we think of a way how we can still sort of save the day and come up with an idea how we can sort of estimate the true population, the true mu, which we will probably never know for sure, but, at least we have something that we can present to our boss. Can we come up with an idea how we can save the day? That's a very good idea. What we could do is actually sample, say, n, sample, let's call it p, up to, God knows what p is, thousands, maybe. And then what we can do is we can calculate the mean. We treat every mean from each sample, we treat that as a data point. We calculate the mean of the means. That is exactly what you just said, isn't it, Callum? Mm-hmm. Yeah? We calculate the sample mean of the sample means. So 178, 175, 172, 174, maybe another 175 or something like that. I do that very, very often. And what we will find is that this mean of the sample means is probably a true reflection of the true population mean. Yeah? But of course, taking 1,000 sample means, each sample has a sample size of, say, 10 students or something like that. Boah, that's a lot of, that's 10,000 students that I have to measure. It's a little bit cumbersome. I just as well can probably measure the same population. Yeah, so it's not, but this is a very good suggestion. Now, the next best thing that we could do probably is we say, we will never know exactly what the population mean is. We have a sort of a good guess, but we don't know what it is. How could we express that?
I don't know.
No? Oh, yes, you do know. You just don't know that you know. We could, for example, say, instead of saying it is exactly 178 centimeters, we could say, we think true population mean is about 175 centimeter. There's a, yeah, 175. Yeah, it passes. That's our best guess. Yeah, sort of. How do we express this about? We can just simply say mu equals 175 centimeter plus minus a bit. Yeah, plus minus a bit. So instead of saying that the true population mean is exactly 175 centimeters, we can actually say it is between 175 minus a bit and 175 plus a bit. Yeah, somewhere in between. We think that there must be the true population. So if we, for example, say, let's say a bit is 10 centimeters, then we would say 175 minus 10 and 175 plus 10. So would be, we think this population mean is between 165 and 185 centimeters. And somewhere in between, we think, or we have a good idea that somewhere in between is the true population mean. This is actually, we are pretty confident that the population mean is there. We will never know exactly where it is, but we are fairly confident. And that's why this is called, what do you think what this is called? I'm sure you have heard the name. It's called a confidence interval. Have you heard about that? Confidence interval? No? No confidence. Oh, cool. Wow. Confidence interval. You've heard about confidence interval? No? Gee whiz, what do they teach you at school? Right? But you get the confidence interval, the concept, yeah? It is defined by what is called a lower bound and, surprise, surprise, an upper bound. So that's our estimate. We say the true population mean is probably somewhere in there. And we then can even say, well, instead of taking lots and lots of samples, all we need to do is say, we just simply take one sample with, say, 10 students and basically transfer that and say, we believe the true population mean is between, and instead of the true population mean, which we don't know, we just take our sample mean of one sample. We just simply take one sample and say is, probably should say between A, is between x bar minus a bit and x bar plus a bit. Somewhere in between. Because we don't know the true population mean, we just take a sample mean. Yeah? That is our confidence interval that we can try to work out. Now, I heard you laughing a little bit when I said a bit, because I don't think this is a technical term. We just add a little bit. This actually, in statistics, this a bit has a name. It's called the margin of error. You've heard about it? Mm-hmm. Yeah, margin of error, abbreviated as MOE. Margin of error just simply means a bit, nothing else. Right, now, obviously, I have sort of skirted around the problem because we still are not any wiser how much this a bit should be. I said, for example, 10 centimeters, but that was just a gut feeling. And when people say to me, oh, I've got a gut feeling, my advice is go to the doctor or go to the toilet or something like that. Can't we put some numbers on it? Would that be possible to calculate this a bit, this margin of error? That would be cool if we could. From just what we've got from the sample. How can we calculate a bit? all the information that we have is from the sample that we have taken, and we assume that the sample is representing the whole population. That's all we have in terms of assumption. So how can we calculate a bit? I tell you after the break. Shall we do a 5-minute break? 5-6 minutes? Yeah? And then we calculate a bit. Okay? Yes, please.
So earlier, when you said the population are in parameters, they're using the Greek symbols.
Yeah.
And then you said the sample statistics use the X bar from mean.
Yeah.
What do they use for the standard deviation?
Excellent. Brilliant question. After the break.
Okay.
Back in about 6-7 minutes, okay?
No one's ever going to forget what the sampling error is now.
Herpes.
I'm looking forward to see it on assignment. Sampling error can be
Like herpes.
it's like herpes.
No, you can't get rid of it. It is there. Now, here is a challenge for you guys. Can you please develop a reliable drug against herpes?
I'll work on it.
Yeah? This will make you probably even more money than Viagra.
I don't know. I still think Viagra would be the.
If you could sort of combine it.
Yes.
I mean, I've heard, for example, that Viagra has other applications.
That no one uses it for.
Yeah. So, for example, if you put Viagra into the water of cut flowers, it stops them from wilting, and this.
Does it really? No.
Makes sense so far, even for the people who have not a lot of statistical exposure? Yeah. Yeah. Yeah, happy with it.
Right. Oh, it's a little bit cold. I'm not touching that though. I feel like I'm definitely going to ruin it.
That's fine. Okay, so what the hell is that? I have absolutely no idea. Honey line. Should be 26.
It'll be 27 in a minute.
Yeah. Yes, please. Need to collect the smokers.
Be careful. Oh, don't you? I know somebody should come from his iPhone. You have a pen. You have a pen.
Mine is free with my phone. Is it good? What's good? Like the packet? Yeah. It's fine. Yeah. I'm not sure if it's inside.
Oh, no, I was going to say, look, Jane is like, oh, something. Gloves. It's expensive. Okay, I've got other kids. I mean, this is so
Shall we close the door, maybe?
yeah.
Yeah, then it's not so cold. Yeah, well, everybody generates about 40 watt of yeah, it's like a light bulb. 40 ohms, so we're warming up. Yes. So, yep, it's mean, isn't it?
It's very mean.
I know, it's a cliffhanger. I do that in all my lectures. Students hate it. Okay, thank you for coming back. Not doing a runner. Let's see how we can calculate this confidence interval, or at least this margin of error, so that we don't have to say a bit, or that we don't have to trust our gut feelings. And just to reiterate, all we can use is actually the data that we get from the sample, because that is all we have. But maybe this is enough to make an educated guess about this confidence interval. Now, first of all, we need to think about what this confidence interval might depend on. And we can do that just simply by not going into hardcore maths, but by just, sort of following our intuition. What does a confidence interval depend on? The first thing, and I will come back to that, what I mean by that, is the confidence interval depends very strongly on the data format. We talked about data format yesterday. And what I'm going to show you in this session is the confidence interval for continuous data. What we are doing is only applicable to continuous data. If you have discrete data, you can't use exactly the same equation that we are going to develop. You have to do a different calculation. And I will show you how to do that later on. So absolutely essential that we have the right information. Let's do the simple things first. It also relies on, and that's very important, the sample size. We call this N. Why? If I just, instead of 10 people, if I just take 3 people and measure the height, then I've got only, 3 measurements. But if I take 1,000 people or 10,000 people, then I've got 10,000 measurements. And the likelihood and the probability that, I take some weird measurements just because by random choice, I picked 3 people who are playing basketball or who are vertically challenged. With these 10,000 people, it will sort of, any extremes will eliminate each other. So they will be more reliable than just picking 3 people. So the bigger my sample size is, probably the smaller my confidence interval has to be, because then I can say it's 175 plus minus 5 centimeters, because I've got already a lot of information about the population, right? So the sample size plays a role. Another thing that plays a role is the variation in the population. The variability of the population. Now, we're probably coming into a slight problem in a moment, but let's not worry about that for the time being. The variability in the population, what does that mean? Let's assume everybody is of the same height. Every apprentice is exactly 175 centimeters tall. So there is no variability in the population. Then of course I can say the true population mean is, I just simply take a sample, and everybody in this in this sample will be 175 centimeters, of course, because that's the population. Everybody in this sample is 175 centimeters, and therefore we can say, well, if that's in the sample, then in the population, it's the same. And we can say the true population mean will be 175 centimeters spot on, because everybody is the same. So if the sample doesn't have any variability, then probably the population doesn't have any variability. Or in other words, the confidence interval will be very small if the population variability is small. The confidence interval will be very large if the population variability is very large. Yeah? So the larger the population variability, the larger the confidence interval. I can't say plus minus 10 centimeters, I probably have to say plus minus 20 centimeters. So now we need to figure out what is the variability of the population. Do we know the variability in the population? What do you think? Do we know the variability in the population? No. It's a little bit like the mean, the true mean of the population. We don't know exactly the population mean, but we said we estimated that. Now, we said we don't know the true variability in the population. That's a bit of a bugger. Without this variability, we can't make any judgment. But maybe we can use the variability of our sample. Yeah? And I've alluded to that earlier already. We can look at the sample and say, what is the variability in the sample? So what is a measure of variability? What did we say yesterday? What did we call it? variance or standard deviation. So what we do is, bless you, we use the standard deviation of the sample to make an educated guess about the variability in the population. Yeah? Now we are doing a guess again. We use a sample statistics in order to guess the true population standard deviation. And I told you the true population standard deviation, that would be sigma because it's a parameter and it's a Greek letter. So we need to come up with a different symbol for the standard deviation of the sample. So we take our data and try to estimate the true population standard deviation. And the symbol for when we do that, when we do this process for the standard deviation is very imaginative, just lowercase s. S is just simply the standard deviation, is an estimate of the true population standard deviation. It's an estimate based on from the sample. From the sample. So we have to estimate this true population standard deviation, and we use the sample for that. But there is a problem again. Oh God, clapper and problems, right? There is a problem. The problem is, let's say I have my 10 students or apprentices, measure their height, and I find that there is a standard deviation in my measurements of, say, 5 centimeters. Right? It's 5 centimeters in this small group. And you've seen how I calculated that yesterday, standard deviation. Question for you. What do you think will be the standard deviation of the population? Will it also be 5 centimeters? Will it be? Could it be smaller than 5 centimeters? With the mean, we said the population mean could be a little bit smaller, could be a little bit larger. For the standard deviation, can it be smaller than our sample, the population? The answer is no, it can't. Because we already know that the lower level of the population variability is what we see in our sample, because the sample represents it. Yeah, makes sense? So we need to do something. We need to sort of do a little bit of mathematical trickery so that our estimated population standard deviation is always a little bit larger than what we've measured. So we need to make that a little bit larger. How do you make something larger? Mathematically. how can you make something mathematically larger? Sorry?
You have to times it by any number for variance.
You can divide, you can times it by a number that is larger than 1. You're absolutely right. If I don't want to multiply it, what can I do?
You can add to it.
Sorry?
You can add to it. Addition.
I can add something, but I like the idea of the multiplication. But if I don't want to multiply it with something larger than 1, I divide it by something lower than 1. You're absolutely right. And you just developed the equation for the variance s squared, that's the variance. And what we do for the variance is we take each observation. Now, we can't take mu because we don't know mu, but we use x bar, our sample mean. We square it. And now we divide by something that's a little bit smaller than previously. And that would be sample size. We just simply subtract 1 of it. Why this 1? Just simply to make this a little bit bigger. We divide by something a little bit smaller, then it makes it a little bit bigger. If we've got a huge sample size, then this -1 doesn't make any difference because we already have a lot of information about the population. But if the sample size is very small, then it makes a big difference because it sort of compensates for it. And of course, S would be just simply the square root of that, xe minus x bar squared divided by n minus 1. This is known in statistics as the sample standard deviation. Should actually be the estimated population standard deviation based on a sample, but nobody says that because it's just too much to write. And what you see is that this standard deviation differs in 2 aspects from what we calculated yesterday. And I've written down the equation. Yesterday, we used this one for the variance with n, the observations. Now, we do n minus 1 because we want to make it a little bit bigger. Yeah? If you want, we can do 1, 2, 3, 4, 5. The mean was 3. X bar is also 3, it's the same as the mean when we treat that as a sample. For sigma squared, we said it is, what did we have? 4, no, 10, no, 15, no, what was it? 10, yeah. 10 divided by 5, yeah, was 2. Now, s squared would be, it doesn't change the top bit, that's still 10, but now we divide it by 4, n minus 1 equals 2.5. Yeah, and you see it adds quite a little bit to it. So that would be our estimated variation in the population. It is a little bit bigger than the one that we just simply calculated here from when we treat our sample as the population, but that is understandable because there is probably even more variability. We just picked a small sample for that. So this estimated population standard deviation is always a little bit bigger than what we just simply calculate from the group of students that we have. Yeah, makes sense? Great. So that is why there are two standard deviations. And of course, in Excel, you can do that very simple. The variance in Excel, I told you yesterday, for this one here is standard deviation dot p. The variance for this one here is standard deviation dot s. Yeah,
Population versus sample.
that is the estimated variation for the population based on the sample. Make sense? Whoa, that was quite something. So for a lot of people, they just simply say, well, I just calculate the standard deviation. And inside me, then goes a sort of a little hedgehog wakes up and it goes like, what standard deviation do you actually want to calculate? Do you want the standard deviation of the data that you have? Then you divide by n. But if you want to do an estimate, then you have to divide by n minus 1. Yeah? Brilliant. So we have the data type, we have the sample size, we have the standard deviation for our confidence interval. And there is one more thing that we need to add. Remember, we did all this fancy stuff just simply to calculate this margin of error, this a bit, the confidence interval. But there's one more thing to add. That is what gave the whole thing the name. How confident do we want to be? How confident do we want to be when we calculate this confidence interval? And that boils down to making decisions. So, for example, we have, let's say, 175 centimeters. That is what we got from our sample. And I can now say, come up, I actually know the true mean. Yeah, I pretend now I know the true mean. Of course, I don't know it, but I pretend to know the true mean. And you have to give me a number where you think that is probably plus minus. What would you say? 10 centimeters? Yeah? How confident are you? You're not confident. Uh-huh.
Plus minus 7.58.
Plus minus 7.58. Yeah. How confident are you?
Decently.
Decently. Oh, that's good. Yeah, I like that. If you want to be more confident, what can you do?
Bigger sample.
Yeah, or you just simply say, if I want to be more confident in my judgment, I just make it bigger. If I say the true mean plus minus 100 centimeters, so it would be between 75 centimeters, the true population mean, and 275 centimeters. In God's name, surely the true population mean must be in there between. So I'm pretty sure that's in between, right? But then on the other hand, if I say 175 plus minus 1 centimeter, how confident can I be that the true mean is there? Probably not a lot, right? I probably make the wrong decision. So it boils down to how confident I want to be. And that is something that traditionally causes a lot of anxiety and stress for people. How do we sort of measure this thing with this confidence thing? It's a confidence thing at the end of the day. And wouldn't it be nice if we had a sort of some numerical thing that we just simply can use for exactly that, to express our confidence? You said plus minus 10 centimeters, you're not really confident about it. You said plus minus 7.58 centimeters, and you are decently confident. I say 1 centimeter, absolutely not confident at all. Wouldn't it be great if we had a sort of a measurement for that? And it boils down to make the right decision. So how do we make right decision? And I want to use an example from absolutely not clinical trials related. But stick with me for a moment, because it hopefully will become clear. We are now going into the murky area of decision making and making the right decision, making wrong decisions. And yesterday, an absolutely disgraceful and heinous crime was committed. I had some chocolates up there. I went to the toilet, and afterwards, the chocolate had disappeared. Absolutely disgraceful. Somebody has nicked the chocolate. Right? Absolutely horrible. So I need to find the guilty person who did that, because they will be punished. He did it. Uh-huh. Now, I tell you, how will this work in a court of law? I tell you that we have a suspect, right? Who nicked the chocolate? Who nicked the chocolate? You did. You did? Did you nick the chocolate?
No, I didn't.
No, of course. She would say that, wouldn't she? Yeah? Was it you? Okay, so we need to investigate. How does an investigation start with? How does a court procedure start with? What is the first assumption? Yes, but you know, we are beyond that point already. Suspect. What does the law say about the suspect? Absolutely right. We say our initial assumption is not guilty. Not guilty. That's our assumption, or that is the assumption of the law. What would be the opposite? Guilty. Nicked the chocolate. That's our assumptions here. Right? By the way, that's the English system. If you go to court in Scotland, there is a third option. Does anyone know? It's called not proven guilty. It means we know exactly that you did it, but we can't prove it, for heck's sake, right? But we do English law. So the assumption is not guilty. Now, we can also say there are two options. She actually committed this crime and nicked my chocolate. So, did it, or she didn't do it. What do you think? Did she do it? No, you're innocent.
Yeah.
Mm-hmm. Okay, now we send out the jury. Well, actually, no, we don't. This is actually the sort of what is called a confusion matrix, because sometimes it's rather confusing what's happening, or a 2x2 matrix that will help us sort of to understand what's going on here. And what we now do is we collect the evidence. So the chocolate is gone. We found some chocolate wrappers in her bag. It's pretty damning, isn't it? Well, it's not the right wrappers, maybe. When I saw her yesterday, she was still chewing on something. She probably eaten my chocolate. So we get evidence. That is exactly what we are doing in statistics. We collect evidence in clinical trials. And so we've collected all the evidence, and now we need to sort of think about what options the jury has. The jury can make two right decisions. So you are the jury, you can make two right decisions. One decision would be, which one would be the right decision when you look at that? at that grid. What do you think? What decision could the jury make? Sorry? She did it and guilty. This would be the right decision. Yeah? Any other? Absolutely right. Did not do it and not guilty. If the jury comes to these conclusions, the right decision has been made. Yeah? True? We have two fields that are empty. Obviously, this is going to be very difficult now because it has consequences. If we say she did not do it, but we convict her, it's the wrong decision. It's an error. Yeah? And because it's in the first column, it's called a type 1 error. Type 1 errors are usually abbreviated with the symbol alpha. We make a type 1 error, or the jury makes a type 1 error. She didn't do it, but we convict her. On the other hand, if she did it, but we let her go, it's the wrong decision, and this is called a type 2 error, abbreviated with beta. In this case, which one do you think is more problematic? Type 1 or type 2 error? What do you feel? The type 1 error. You would be seriously pissed off if you had to go to jail for something that you didn't do, right? So type 2 is not so important in this case. Type 1 error is absolutely, we need to avoid that. So we need to have pretty damning evidence to make a guilty verdict, because the guilty verdict has far more consequences than, say, a type 2 error. We just let her go. She's laughing in the, on the way out, probably eating more chocolate that she nicked, but we couldn't do anything to her. So I would say my way of saying sorry. Do you like chocolate? Awesome. Say, we've got 4 squares, take 4. Thank you very much for being my guilty party. So, what we need to do is, in our decision making, we need to try and keep this type 1 error as small as possible so that we don't make the wrong decision. So keep alpha small. So that we don't make the wrong decision. Beta, yeah, but in this case, it's not really a big problem. It depends on the context sometimes, yeah? Sometimes we want to keep alpha small. Beta, we don't worry too much. Sometimes we want to keep beta small and we don't worry too much about alpha. And alpha and beta are actually somehow related to each other. But this is what we need to make sure that we don't make the wrong verdict. In the jury system, usually keep alpha small means we only make a wrong decision, say, every 1,000 times, let's say. Very rarely will we convict somebody who is not guilty. You can tell I have faith in the jurisdictional system. In statistics, we are a little bit more relaxed, but we can actually say whatever value for this alpha we want, that is what we are going with. And it turns out that very often a good value for this alpha, it's also called the significance level, is set to 5%, which is the same as 0.05. That means I assume that in 5% of my decisions, I'm wrong. I'm willing to accept that I'm wrong in 5% of the decisions. Now, if you ask my wife, she will tell you that my alpha, my significance level, is probably around 100% because I'm always wrong. So that's her set. I believe that, yeah, she might be right. I am wrong occasionally, but it's really occasionally. So my alpha is personally 1 in 10,000 times. The rest of the time I'm right. But, you know, valuing peace, I would not challenge her. I would say to her, yeah, you are right, darling. Yeah, it is. The biggest regret in my life is actually that I didn't listen to my wife. And then people ask me, what did she say? And I say, I don't know. I didn't listen. So, yeah. So, very often we set alpha, the significance level, to 5%. In other words, 5% of the time we make the wrong decision. Or I can also say 95% of the time I make the right decision. Yeah, makes sense? And that is exactly what we talk about when we talk about the confidence level. Confidence level. The confidence level is actually 100% minus alpha. So in this case, if we set alpha to 5%, our confidence level would be 95%. We want to set everything so that we are 95% sure. We want to build the confidence interval so that 95% of the time we actually make the right decision. Make sense? Yeah? This is alpha, this is the significance level. Whoa, that was hardcore, right? Absolutely essential concept that you understand this type 1 error, this significance level, because we will need it later on in the afternoon, because we will compare our sort of the evidence that Hope was guilty or not guilty. Okay, so now how on earth do we calculate this? How do we put all these factors together? Now, if we've got continuous data, and it needs to be continuous in this case, we can say this margin of error is actually calculated as, say, I call it a critical factor. What this factor is, I will say in a moment. Critical factor times, what did we say? We need the standard deviation. And we can make it smaller if we've got a larger number. We divide it by the square root of the sample size. There are reasons why it's the square root. Don't stress too much about it. So this is the estimated population standard deviation. N is the sample size. And actually, this whole thing here, this S over square root n, because it appears so many times in statistics, has even a name. It's called the standard error of the mean, or abbreviated as SEM, standard error of the mean. Now, all we need to do now is to try and figure out what is this stupid critical factor. And this critical factor that we are looking at here is actually a number that includes our confidence interval, or includes our, not confidence interval, that was wrong, includes the confidence level. So this 95% includes this 95%, and is a sort of an additional, a number to make this equation work in a way. How do you find that? This factor also includes a little bit the sample size. And to top it all, it includes information about the population, how the population looks like. it still hasn't solved our problem, right? What does he mean? What does the population look like? Now, a population, and we don't know that, do we? We don't know, for Pete's sake. We have no idea what the population looks like. We just make assumptions here. But luckily, when we are working with continuous data, very often we find that when we look at the population, they look all pretty much the same. They have a similar sort of distribution. And when we draw the distribution of the population, population distribution, what we find, for example, the height of people, what we find is that there will be a few people who are diddy. There are a few people who are large, or tall, I should say, not large. But most people are sort of in between, yeah, in the middle. And when we draw such a distribution, we would find sort of something like that. You've seen something like that before. It's the famous bell curve, because it looks like a bell. What this curve tells us is, here, the top, that would be the population mean. Most people are around this mean. There are only a few people, here that would be the height. There are only a few people who are taller, and there are only a few people who are smaller than this area. So it's a nice and it's a symmetric curve. It basically assumes that the number of very tall people is pretty much the same or similar number to the number of people who are small. Yeah, nice symmetrical curve. But it's not just any curve. This is also called the normal or bell or Gaussian curve. The equation for that is horrendous, and I'm not showing it to you because it's just simply not worth it. I can't remember it anyway. But this bell curve, this Gaussian curve, has a few properties that make it absolutely brilliant and unique. And many, many measurements that we can think of in nature are actually based on this normal, what we call distribution. What is so special about it? Well, we can say if we move one standard deviation to the left and to the right, it's probably here, one standard deviation in the population, if we move left and right of the mean, we've got this point here and this point here, right? Something like that. And when we check how many people are in this range, how many people are in this range, one standard deviation above and one standard deviation below the mean, we find that this number is roughly 68%. So 68% of people would be in this 1 sigma range. 1 sigma to the left, 1 sigma to the right. We can even go further and we can say, what if we have 2 sigma then we have this area here. It's getting very colorful. Right? We've got this red area. And in this area, in this red area, we have roughly 95% of people. As I said, height, weight, all these things. We can even go further. And oh yes, let's do a green one. Yeah, and somewhere here. So that would be, and the green one, that would be 3 sigma. And here's 3 sigma. This would contain 99.7%. You have probably seen on Facebook, no, you are the younger generation, you don't use Facebook, right? Facebook is, you do? Oh, I thought, my kids told me that Facebook is only for the old people. So no offense intended, right?
Guaranteed they'll get a Facebook when they get older.
Sorry?
Guaranteed they'll get Facebook when they get older.
They have Facebook, but they don't use it. It's Instagram, Snapchat, and all this TikTok. Yeah, it's crap. But you see that IQ is normal distributed, and we actually write IQ is normal distributed n. That's the or. Sometimes you see it with a squiggly line. It's normal distributed with a mean and a standard deviation. The mean is 100, and the standard deviation is 15. That's the population. And you sometimes see that. And you can now ask yourself, given that this is sort of here our distribution, our IQ distribution, for example, let's call it IQ here, we can ask the question, how many people, or what percentage of people are between, here is 100, here would be 115, and here would be 85. So 1 standard deviation to the right, 1 standard deviation to the left. How many people have an IQ between 115 on top and 85? How many? 68%. How many people have an IQ between 70 and 130? 95%. So I was recently asked, what is your IQ? And I said, I have absolutely no idea, but I assume it is between 70 and 130. Actually, my error would be 5%. 95% of the people are in that range, and there's only a 5% chance that I'm wrong with that. Yeah. Remember, 5%. That would be my error in making the decision where I am. Yeah. I can also even say, okay, I've got 100 and let's say I've got 130 IQ. I wish. IQ is 130. How many standard deviations am I away from the mean? How many standard deviations away from mean? And you're absolutely right. It is, answer is 2 standard deviations, right? What you just did was you calculated what is called a z-score. The z-score is defined as your observation minus the mean divided by the standard deviation. Yeah? Now I can, for example, say we've got some politicians, and being politicians, I hope nobody has any relatives who are in politics, because it will be rather damning what I'm saying. But you know, some politicians have an IQ that is probably level to the IQ of 250 grams of steamed broccoli, right? So if we've got a person, say, an IQ of, say, 60, which is barely alive, I can calculate the z-score. This would be 60 minus 100 divided by 15, and that is negative 40 divided by 15, and I can't do that in my head, but you get the gist. So the z-score can be positive, can be negative. Yeah, makes sense? So this is a typical characteristic of a normal distribution. Normal distributions are incredibly common in nature, as I said, IQ, and it does not just rely on humans. If you, for example, measure the size of a dog, the length of a mouse, plants, blood pressure of a tortoise, things. Do tortoises have blood pressure? They must have. Yes. So a lot of things follow the normal distribution. I lied to you, however, I have to say, because it's not exactly true. This 95% is roughly true, but the exact value, it's a very long number, is 1.96 standard deviations. Right. Now, what we can do now for our confidence interval is we can say confidence level 95%. So we can write our margin of error equals the critical factor. This includes this 95% confidence, and it would be 1.96 times our standard deviation. In this case, we use the standard deviation where we know it already. Standard deviation over n. So we can say we take our sample, x bar, plus minus 1.96 times the standard deviation divided by square root n. And that would give us roughly an idea of the margin of error, where we can be 95%, where we can be fairly sure, actually, that the true population mean is within this range. So now you can actually calculate that and say, I'm far more confident now with this assumption. That makes sense. Yeah. This is how you can calculate a confidence interval, at least in theory. There's one level of complexity, and I know you are going to hate me for that. There's one level of complexity. But before we tackle that level of complexity, we probably should have lunch, right? And stretch. Lunch, yes? I'll be back at 2. You'll be back at 1?
1 o'clock.
1, you, I'll be back at 2. Does that make sense, what I did? Confidence level. Confidence interval. Confidence interval tells us how much we should add to our sample mean to get the true population. Yeah? See you later. See you after lunch. Try to recover. It's, brain buzz.